The discovery of an object from outside our solar system is sparking debate in the scientific community.
An object from outside our solar system just did something that breaks physics. NASA says it's a normal comet. But 48 hours after passing the sun, it turned blue. Not red like every other comet in history. Blue. That means parts of this object are glowing hotter than the surface of the sun. And there's no natural explanation for that. Harvard's top astrophysicist just went on national television with a warning. We might be watching something artificial. And the proof arrives in days. The object is called 3I Atlas. The 3I means it's the third confirmed visitor from beyond our solar system. The first was Oumuamua in 2017. That one caused controversy because it accelerated without any visible propulsion and had a shape unlike any natural object we'd ever seen. Avi Loeb suggested it might be artificial. The scientific establishment called him reckless. Then Oumuamua left our solar system forever, taking its secrets with it. The second interstellar visitor was 2I Borisov in 2019. That one behaved exactly like a normal comet. Ice, dust, predictable tail, nothing strange. It proved that not every visitor from deep space is weird, which makes what's happening with 3I Atlas even harder to ignore. Because 3I Atlas isn't behaving like 2I Borisov. It's behaving like nothing we've documented before. Discovery happened on July 1, 2024, when the Atlas survey system picked up a faint moving object. Within weeks, astronomers calculated its trajectory and confirmed what made it special. This thing came from interstellar space. It entered our solar system from the direction of Sagittarius, the same region where the famous WOW signal originated in 1977. A radio transmission so strong that scientists thought it might be alien communication. It never repeated. We never got answers. 48 years later, something physical arrives from that same patch of sky. NASA tracked 3I Atlas as it fell toward the sun. They ran the models. Standard comet behavior predicted. As it approaches, solar heat warms the surface. Ice turns to gas. Dust gets released. The object should brighten gradually and develop a tail. Temperature maxes out around 200 to 400 Kelvin depending on distance. That's cold, far colder than anything that glows. October 29th, perihelion. Closest approach to the sun at 203 million kilometers. The SOHO spacecraft's cameras capture the moment. Scientists begin analyzing the images. And that's when someone notices the color. Comets glow red or neutral, always. The dust they shed scatters sunlight but appears reddish because of particle size. The nucleus itself stays too cold to emit visible light on its own. Every single comet ever observed follows this pattern, hundreds of them, thousands of observations, perfect consistency, until 48 hours ago. 3I Atlas is glowing blue, not just a little blue, not a trick of the camera, bluer than the sun itself. Stephen Burns, a geophysicist tracking the object, puts it simply. We have just observed interstellar object 3I Atlas brightening dramatically over the past few days. But there's no real significant tail like you would get from a normal comet, so it's still quite bizarre. Avi Loeb goes further. Appearing on the Rising News program, he doesn't hedge. The question is, what is going on? You need to arrange a temperature somewhere on the object which is higher than the temperature of the sun in order for it to be bluer than the sun. Higher than the temperature of the sun. Think about what that statement means. Because the physics behind it changes everything. Every object in the universe that has heat emits light. This is called black body radiation. It's one of the most basic rules in physics. The hotter something gets, the more energy it releases. And that energy comes out as light. Here's the key part. The color of that light tells you the temperature. Think about a piece of metal heating up. At first, it's just warm. You can't see any glow. Keep heating it. Eventually, it starts glowing dull red. Heat it more. The red gets brighter, then shifts to orange. Keep going. Orange becomes yellow, then white, then blue-white. The hottest stars in the universe glow blue. The coolest stars glow red. Same principle. Temperature determines color, always. Our sun sits in the middle, surface temperature of 5,800 Kelvin. That's about 5,500 degrees Celsius. Hot enough that the metal example doesn't even apply anymore. At that temperature, things don't just glow. They radiate enormous amounts of energy. And the sun's peak emission comes out as yellow-white light. That's what 5,800 Kelvin looks like. Now here's where it gets important for 3I Atlas. Natural comets are cold. They're chunks of ice, rock, and frozen gases that have been drifting through the freezing void of space for millions or billions of years. When they approach the sun, solar radiation heats their surface. But that heating is limited by distance and basic physics. At Earth's distance from the sun, we receive about 1,360 watts of energy per square meter. That's enough to warm the planet, drive our weather, make life possible. But it's not enough to make rocks glow on their own. 3I Atlas at perihelion was 203 million kilometers from the sun. That's about 1.36 times Earth's distance. And here's where the inverse square law matters. The farther you are from a light source, the less energy you receive. Not just a little less, dramatically less. Double the distance, you get 1/4 the energy. It drops off fast. At 3I Atlas's distance, solar energy hitting the surface maxes out around 770 watts per square meter. That's about 56% of what Earth gets. And Earth's surface doesn't glow blue. It doesn't even glow at all. But wait. Comets have another factor. They're not solid. As they heat up, ice turns to gas. That process, called sublimation, actually cools the surface, like sweat evaporating from your skin. The phase change pulls heat away, so even with direct sunlight, comet nuclei stay cold. Measurements from every comet mission we've ever sent show surface temperatures between 200 and 400 Kelvin. That's -73 to +127 degrees Celsius. At those temperatures, objects don't emit visible light, they're too cold. What we see when we look at comets is reflected sunlight bouncing off dust particles, and that dust scatters red wavelengths better than blue, which is why comets appear reddish or neutral colored, never blue, because blue means hot, really hot. For an object to glow blue, to emit blue light from its own heat rather than just reflecting it, the surface needs to exceed the sun's temperature. We're talking 6,000 Kelvin or higher. That's the only way the peak emission shifts far enough into the blue part of the spectrum that the object appears bluer than the sun. There is no natural process that heats a comet nucleus to 6,000 Kelvin at 200 to 3 million kilometers from the sun. Solar radiation can't do it. The math doesn't work. The energy isn't there. And yet the SOHO images show exactly that. Blue light, bluer than the sun, which means something on 3I Atlas is generating heat internally. Something is producing temperatures that solar heating alone cannot explain. And when Avi Loeb ran the calculations, he found out exactly how hot we're talking. Avi Loeb isn't just any scientist making claims. He's the former chair of Harvard's astronomy department. He founded the Black Hole Initiative. He's published over 1,000 scientific papers with more than 100,000 citations. He's advised governments, led major research projects, and spent decades at the top of his field. He's also controversial because in 2018, when Oumuamua's data showed that strange acceleration with no visible propulsion, Loeb did something most scientists avoid. He suggested we should seriously consider the possibility it was artificial. A light sail. Technology from another civilization. The backlash was immediate. Other astronomers called him irresponsible, said he was chasing headlines. that he damaged his credibility by even mentioning aliens. But Loeb didn't back down. He wrote a book, started the Galileo Project specifically to search for technological objects in space, built telescope arrays, committed resources, put his reputation fully on the line. Which is why when he goes on national television and talks about 3I Atlas, people pay attention. Like it or not, he's forcing a conversation that mainstream science would rather avoid. And the numbers he's presenting aren't speculation, they're measurements. On Rising, Loeb explains what the blue color means in exact terms. That's huge. That's 20 times the temperature on Earth right now. 20 times. Earth's average surface temperature sits around 15 degrees Celsius. 20 times that gets you to 300 degrees Celsius. Except Loeb isn't talking about Celsius when he says 20 times. He's talking about absolute temperature, Kelvin scale. Earth averages about 288 Kelvin. 20 times, that is 5,760 Kelvin. Almost exactly the sun's surface temperature. And remember, for something to appear bluer than the sun, it needs to exceed that temperature. We're talking about an object that should be frozen. An object receiving barely half the solar energy that Earth gets. An object made of ice and rock, according to NASA. Somehow running at temperatures above 6,000 Kelvin. Loeb makes the problem clear. You need to arrange a temperature somewhere on the object which is higher than the temperature of the sun. The word arrange is deliberate, because natural processes don't arrange temperatures. They follow predictable patterns based on energy input. Solar heating at that distance produces maybe 400 Kelvin max. Something else is generating heat. Something internal, something powerful. But that's just the temperature problem, because the brightness data reveals something even stranger. Comets brighten as they approach the sun. That's normal. We've studied this for over a century. Scientists have models that predict how bright a comet will get based on its size, composition, and distance from the sun. These models work. They're accurate within small margins because the physics is well understood. Until October 29th, those predictions held for 3I Atlas II. A research paper published by astronomers Kei Chenzong and Carl Battams analyzed images from the SOHO spacecraft. SOHO is a solar observatory launched in 1995. Its main job is watching the sun, not hunting comets. But its coronagraph, a special camera that blocks the sun's bright disk, can capture objects passing near our star. Between October 15th and October 29th, SOHO tracked 3I Atlas as it approached perihelion. The researchers used advanced stacking techniques to pull signal from noise. They built brightness curves showing how the object's light output changed over time. The models predicted 3I Atlas would reach magnitude 9 at closest approach. That's a brightness measurement. Lower numbers mean brighter objects. Magnitude 9 is bright for a comet, but not extraordinary. Visible through good binoculars under dark skies. The actual observation showed magnitude 7.5. That difference matters more than it sounds. The magnitude scale is logarithmic. Each whole number represents about 2.5 times more light. A difference of 2.5 magnitudes means the object is roughly 4 times brighter than predicted. 4 times. Comet brightness models aren't guesses. They're based on thousands of observations. Decades of data. When predictions miss by 4 times, something unexpected is happening. Stephen Burns tracked this in real time. On his analysis, he notes the strangeness immediately. The object brightened dramatically, yes, but there's no significant tail. Normal comets develop tails as they approach the sun. Ice vaporizes. Gas streams away. Dust gets released. That material reflects sunlight and creates the classic tail structure we associate with comets. 3I Atlas brightened without that signature. The light is coming from the object itself, not from a cloud of surrounding material. Burns is careful with his words. Whether this is a comet or an object or whatever, it's really totally open. There's so many bizarre things that to classify it just 100% this is what it is at this point, I think is a little preemptive. The compositional analysis adds another layer. Spectroscopic data, measurements of what wavelengths of light the object emits or absorbs, show differences from normal comets. The exact makeup doesn't match what we expect from ice and rock that formed in our solar system, or even from other star systems if we assume similar formation processes. It's not wildly different, just off. Enough to notice, enough to question. SOHO's instruments have limitations. The spacecraft is old. Its cameras weren't designed for detailed comet studies. Image processing involves stacking multiple exposures, which can create artifacts. Maybe the blue color is an artifact. Maybe the brightness measurements are skewed by technique. Except SOHO has discovered over 5,000 comets. None of them ever showed up blue. None of them brightened this far beyond predictions. None of them survived what happened next. Because while 3I Atlas was approaching the sun itself was doing something it hadn't done in decades. The far side of the sun was exploding. Throughout late October 2024, massive sunspot groups formed on the hemisphere we couldn't see from Earth. Some of these spots were larger than Earth itself, dark regions where magnetic fields twisted and built up energy. And when those fields snapped, they released that energy all at once. X-class solar flares, the strongest category, each one a violent eruption releasing more energy than billions of nuclear bombs. The flares sent electromagnetic radiation screaming across space at the speed of light. But that wasn't the dangerous part. The dangerous part came next. Coronal mass ejections, CMEs. Think of the sun's outer atmosphere, the corona, as a sea of superheated plasma, electrically charged particles held in place by magnetic fields. When those fields break, billions of tons of plasma get hurled into space. These aren't gentle releases. CMEs travel at millions of kilometers per hour. They carry temperatures of millions of degrees. And they pack enough electromagnetic energy to destroy satellites, fry electronics, and knock out power grids when they hit Earth. Between October 21st and October 29th, at least 6 massive CMEs erupted from the sun's far side, and 3I Atlas flew directly through them. October 21st marked superior conjunction. That's when an object passes on the far side of the sun from Earth's perspective. The alignment was exact. Earth, Sun, 3I Atlas in a straight line. The same type of alignment that triggered the Halloween storms in 2003. That event, one of the most intense solar outbursts ever recorded, caused auroras as far south as Hawaii and damaged spacecraft across the solar system. This time, the storms were just as powerful, maybe stronger, and they hit 3I Atlas during its closest approach. Here's what should have happened. A natural comet nucleus is fragile. Ice, rock, frozen gases, loosely held together by weak gravity. When a CME strikes, the plasma wave compresses the magnetic field around the object. That induces electrical currents in any conductive material. The currents generate heat, extreme heat. And the radiation pressure from billions of tons of plasma hitting at supersonic speeds creates mechanical stress. Comets fragment under far less. We've watched it happen. Comet Shoemaker-Levy 9 broke into more than 20 pieces just from Jupiter's gravity. Comet Linear disintegrated as it approached the Sun in 2000. Comet Ison didn't survive perihelion in 2013. These objects fall apart easily. A direct hit from 6 major CMEs should have torn 3I Atlas to pieces. The plasma should have stripped away surface material, flash vaporization, explosive outgassing. The nucleus should have either fragmented entirely or at minimum lost significant mass and created a spectacular debris cloud. That's not what happened. 3I Atlas survived, intact. No fragmentation, no debris field, no catastrophic outgassing event. Instead, it brightened. 4 times more than models predicted, and it started glowing blue. Stephen Burns calls it a stress test, an unintentional experiment where the sun itself tested whether this object is what NASA claims. Ice and rock don't survive that bombardment intact. They can't. The physics doesn't allow it. But what if the object isn't ice and rock? What if it has conductive structures, systems that can absorb electromagnetic energy, materials designed to withstand extreme conditions? When a CME hits a conductive object, it induces powerful electrical currents. Those currents flow through the material. They generate heat. If the object has systems trying to dissipate that energy, trying to manage the surge, those systems would glow. They would produce thermal emissions. And if they were overloaded, struggling to handle more energy than they were designed for, they might glow blue from the excess heat. That's exactly what the observations show. Blue light, dramatic brightening, intact structure, survival through conditions that should have been lethal. The timing is too exact, the correlation is too strong, and the object's survival reveals something about its nature that size estimates make even more impossible to explain. When Avi Loeb estimated the size of 3I Atlas, the numbers didn't make sense. Based on how much light the object reflects, based on its brightness at various distances, the calculations point to something enormous. The size has to be at least the size of Manhattan Island, Loeb stated. That's roughly 10 to 15 kilometers across, and the mass needed to maintain its current trajectory while losing material comes out to at least 30 billion tons. 30 billion tons. For perspective, the International Space Station weighs about 420 tons. 3I Atlas is 71 million times more massive than humanity's largest space construction. This isn't a small rock. This isn't a house-sized boulder tumbling through space. This is a mountain. And that creates a statistical problem that nobody wants to address. Interstellar objects should follow a size distribution. Lots of small ones, fewer medium ones, very few large ones. It's basic probability. The same reason there are more pebbles than boulders on a beach. We should have detected hundreds of small interstellar visitors before finding one this massive, but we haven't. Oumuamua was first, about 400 meters long. 2I Borisov was maybe a kilometer across. Then 3I Atlas shows up at 10 to 15 kilometers. The pattern is backwards. Unless the large ones aren't random, unless they're targeted. Loeb raises this exact point. Why haven't we found millions of smaller objects before we find this giant one? The size distribution is inverted, unless the giants aren't random. Then there's the trajectory. 3I Atlas didn't just wander into our solar system. Its path is nearly aligned with the plane where all the planets orbit: Earth, Mars, Venus, Jupiter. We all circle the sun in roughly the same flat disk. Most objects coming from interstellar space would approach from random angles: up, down, sideways. Three-dimensional space offers infinite approach vectors. The chance of a random object naturally aligning with the planetary plane? 1 in 500. Loeb doesn't call it proof, but he asks the question directly. It looks as if it came along the plane of the planets around the sun. The chance of that happening at random is 1 in 500. The question arises as to whether this trajectory was planned as part of a reconnaissance mission. Reconnaissance. The word is deliberate, because the trajectory doesn't just align with the planetary plane. It brings 3I Atlas unusually close to Mars, Venus, and Jupiter, closer than random chance would predict. Almost like the path was calculated to maximize observation opportunities. And then there's the composition. Spectroscopic analysis shows nickel, lots of nickel, but very little iron. That ratio is backwards from every natural object we've studied. Asteroids are mostly iron with some nickel mixed in. A typical ratio might be 90% iron, 10% nickel. Meteorites follow the same pattern. It's what you get when metals condense from a stellar nebula. 3I Atlas appears to be mostly nickel with minimal iron. Loeb points out where we do see that composition. The only place where we have such a composition is nickel alloys produced industrially for aerospace applications. Inconel, Monel, Hastelloy. These are engineered alloys, nickel-based materials designed to resist extreme heat, corrosion, and stress. They're used in jet engines, rocket nozzles, nuclear reactors. Anywhere you need metal that won't fail under brutal conditions. Exactly the kind of conditions you'd face if you were building something designed to survive close approaches to stars, something designed to endure solar storms, something built to last. The object is losing 150 kilograms of material every second as gas streams away. But with 30 billion tons of mass, that loss is negligible, like a human losing a few skin cells. The trajectory stays stable. The object maintains course. And in less than a week, humanity gets its closest look yet. The European Space Agency launched the JUICE spacecraft in April 2023, Jupiter Icy Moons Explorer. Its mission had nothing to do with interstellar objects. JUICE was designed to study Europa, Ganymede, and Callisto, 3 of Jupiter's moons that might harbor liquid water beneath ice shells. The search for life in our own solar system. The spacecraft is currently in the cruise phase. It won't reach Jupiter until 2031. Right now, it's performing gravity assists, using planetary flybys to adjust trajectory and build speed. Earth, Venus, Earth again. A carefully choreographed dance through the inner solar system. And on November 2nd, 2024, JUICE's path brings it within 64 million kilometers of 3I Atlas. That's close. Not close enough to see surface details, but close enough for instruments designed to study distant moons to get a clear look at an interstellar visitor. ESA saw the opportunity and took it. They reprogrammed the observation schedule, pointed every sensor at the object. JANUS, the Visible Light Camera System. It'll capture images across multiple wavelengths. If the blue glow is real, JANUS will document it. Not processed stacks like SOHO. Direct imaging, MAGIS, an infrared spectrometer. This instrument measures heat signatures. It can detect temperature variations across the object's surface. If something is generating 6,000 Kelvin heat, MAGIS will find it. The data will show exactly where the hot spots are, how large they are, whether they're concentrated in specific areas or spread across the entire nucleus. SWI, the submillimeter wave instrument. It detects molecules and measures composition. This will confirm or refute the nickel-rich, iron-poor readings. It'll tell us what gases are coming off the object and in what quantities. 3 different instruments, 3 independent measurements, all pointing at the same target. The timeline accelerated. Originally, the flyby was scheduled for November 4th. ESA moved it to November 2nd, 2 days earlier. The exact reason for the change hasn't been publicly stated, but the result is clear. JUICE observes 3I Atlas, while the object is still relatively close to the Sun, while it's still active, while whatever is causing the blue glow is still operating. Data won't be immediate. JUICE is far from Earth. Communication bandwidth is limited. The spacecraft prioritizes storing data on board for later transmission. Full download won't happen until February 2025, when JUICE reorients its high-gain antenna toward Earth. But unlike other observations that disappeared into classified archives, ESA has committed to releasing JUICE data publicly. The images will go into open databases. The spectroscopic measurements will be available for any scientist to analyze. There will be no suppression, no hiding anomalies behind national security classifications. This is our chance. The closest, most detailed observation of an interstellar object in human history, with instruments designed for scientific precision, not military reconnaissance. And what those instruments find will force a decision that science can no longer avoid. The blue color is different from every other anomaly. Here's why. Trajectory can be interpreted multiple ways. Maybe it's planned. Maybe it's coincidence. You can argue statistics, but statistics aren't absolute proof. Composition is similar. Nickel-rich materials exist in nature. Rare, but possible. Maybe 3I Atlas formed in unusual conditions around a dying star. Maybe neutron-star mergers created exotic ratios we haven't seen before. Brightness? Models can be wrong. Maybe we don't understand comet behavior as well as we think. Maybe there's outgassing we can't detect. Maybe the nucleus is larger or more reflective than estimates suggest. All of these anomalies have wiggle room, space for interpretation, room for unusual but natural explanations. Blue light doesn't. Color is physics. Temperature is measurable. Objects either emit blue light because they're hot enough or they don't. There's no interpretation, no model uncertainty, no maybe. If JUICE confirms that parts of 3I Atlas are glowing at temperatures exceeding 5800 Kelvin, then something is generating that heat. And at 203 million kilometers from the Sun, solar radiation cannot be the source. The energy isn't there, the math doesn't work. Which means internal heat generation. Something inside the object producing enormous thermal energy. Now, there are natural processes that could cause blue light around a comet, and we need to be honest about them. Fluorescence. When ultraviolet light from the sun hits certain gas molecules, they absorb the energy and re-emit it as visible light, sometimes blue light. Carbon monoxide ions do this. We've seen blue ion tails on comets before. Hale-Bopp in 1997 had a beautiful blue tail alongside its white dust tail. Rayleigh scattering. The same process that makes Earth's sky blue. Small particles scatter blue wavelengths more efficiently than red. If 3I Atlas is releasing very fine dust, that dust could scatter sunlight and appear blue. These are real mechanisms. They produce blue color, but they don't produce heat. Fluorescence is reflected and re-emitted solar energy. The molecules aren't hot. They're just glowing from absorbed UV light. The gas itself stays cold. And Rayleigh scattering is pure reflection. The particles don't generate any heat at all. For an object to appear bluer than the sun itself, the thermal emission has to be blue. Black body radiation, heat glow. And that requires temperatures above 6,000 Kelvin. There's no natural mechanism for that. Not at this distance. Not with this energy input. So when JUICE sends back its data in February, we're looking at 3 possible scenarios. Scenario 1. Blue confirmed. MAGIS measures temperatures exceeding 5,800 Kelvin. Multiple hotspots across the surface. Heat signature is real, persistent, and unexplained by solar heating. At that point, artificial origin becomes the leading hypothesis. Not proven beyond doubt, but the explanation best supported by evidence. Scenario 2. Blue was transient. JANUS images show normal colors now. MAGIS reads temperatures in the expected 200 to 400 Kelvin range. The blue glow was temporary, caused by the CME impacts. Some kind of electromagnetic interaction we don't fully understand but not ongoing. Natural explanations remain viable, though the mechanism stays unclear. Scenario 3. Ambiguous data. Maybe elevated temperatures, but not extreme. Maybe unusual spectral features, but not definitive. The object still shows oddities, but nothing that forces a conclusion either way. Scientists continue debating. No resolution. Based on the pattern so far, based on how consistently 3I Atlas has defied expectations, Scenario 1 seems likely. But here's what changes if it's confirmed. If JUICE data shows impossible temperatures, if the heat source is real and unexplained, the burden of proof shifts. It's no longer on Avi Loeb to prove artificial origin. It's on mainstream science to explain what natural process generates 6,000 Kelvin temperatures on a comet nucleus that should be frozen. They won't be able to, because no such process exists. Not in any textbook, not in any model, not in any previous observation of any comet ever studied in over a century of astronomy. And if that happens, protocols activate that have never been used. The UN Office for Outer Space Affairs has guidelines for exactly this scenario: contact, verification, international coordination, response. But there's one more piece, one more connection that makes the timing almost too perfect to be chance. October 2003. 21 years ago, scientists called it the Halloween storms. Late October, massive sunspot groups appeared on the sun's surface, larger than anything seen in years. They erupted with X-class flares, multiple coronal mass ejections, one after another. The barrage lasted for days. The trigger was superior conjunction. Mercury passed behind the sun from Earth's perspective. The alignment was exact, and the sun went wild. Geomagnetic storms reached G5 extreme, the highest level. Auroras appeared in Florida, in Texas, in Hawaii. Power grids failed across Sweden. Satellites lost orientation. The Mars Odyssey spacecraft had to shut down instruments to avoid permanent damage. Airlines rerouted flights away from polar regions, where radiation spiked to dangerous levels. It was one of the most powerful solar events in modern history, and it started when Mercury aligned. October 21st, 2024, superior conjunction again. This time 3I Atlas passing behind the sun. The alignment exact. And within hours, the far side of the sun erupted. 6 massive CMEs in 10 days. X-class flares. Solar activity levels matching or exceeding the Halloween storms. The timing is identical. Superior conjunction, then bombardment. Stefan Burns noticed this immediately. He tracked the sunspot groups, watched them grow, measured the energy output, and he recognized the pattern. What's happening right now with 3I Atlas is almost identical to what happened in October 2003. Coincidence? Or does 3I Atlas, like Mercury, have properties that interact electromagnetically with the sun? Mercury has a magnetic field, weak but present. When it passes close to the sun during superior conjunction, that field interacts with the sun's magnetic structure. It can trigger instabilities, release built-up energy. Does 3I Atlas carry a magnetic field? Does it have conductive structures that couple with solar plasma? We don't know, but the correlation exists. Superior conjunction on October 21st. First massive CME within hours. Continued bombardment through perihelion on October 29th. And those same sunspot groups are still active. They're rotating toward Earth right now. In days, they'll be facing us directly. And if they continue producing CMEs, if they maintain this energy output, Earth faces the same bombardment that 3I Atlas just survived. G5 geomagnetic storm conditions, power grid failures, satellite damage, GPS disruptions, everything our modern infrastructure depends on, suddenly vulnerable. Burns is forecasting possible extreme conditions in early November, the same scenario as Halloween 2003. Except now we have more satellites to lose, more dependence on technology, more infrastructure at risk. But here's the deeper question. If 3I Atlas is artificial, if it's designed to study our sun and planetary system, then it just witnessed the most dramatic solar outburst in decades. It experienced the ultimate stress test, and it survived. It showed us exactly what it's capable of. Was that intentional? Was the trajectory calculated to intersect with these storms? Was the timing planned? We can't know. But we can ask why this object is here at all. The Drake equation estimates how many intelligent civilizations exist in our galaxy. The numbers vary depending on assumptions, but even conservative estimates suggest billions. Billions of civilizations over the 13.8 billion year history of the universe. Most stars formed before our sun. The galaxy is ancient. If intelligent life emerged around older stars, if they developed technology, if they sent probes to explore, those probes have had billions of years to spread. Voyager 1 is humanity's most distant spacecraft. Launched in 1977, it's currently 24 billion kilometers from Earth, moving at 17 kilometers per second. At that speed, Voyager would cross the entire Milky Way galaxy in less than a billion years. There's been more than enough time for self-replicating probes from ancient civilizations to reach every star system in the galaxy, including ours. The Fermi paradox asks, where is everybody? If the galaxy is full of civilizations, why haven't we seen evidence? One answer: we've been looking the wrong way. We've spent 60 years listening for radio signals, building giant telescopes to catch electromagnetic transmissions. But maybe advanced civilizations don't broadcast. Maybe they send probes instead, physical craft, autonomous explorers that arrive, study, and move on. And when they do, we classify them as comets. We file them under natural phenomena. We don't have protocols for technological visitors because we've never seriously considered the possibility. That's what Avi Loeb means by institutional blindness. NASA tracks asteroids that might hit Earth. They have programs, funding, detection systems, mitigation plans. But NASA doesn't think about technological objects in space. Loeb stated it plainly. NASA is not the most accomplished space agency in the Milky Way galaxy since the Big Bang 13.8 billion years ago. It would be arrogant to claim that NASA is the only agency polluting space with technological objects. He's not saying 3I Atlas is definitely artificial. He's assigning 30 to 40% probability based on accumulated evidence. That's not fringe speculation. That's a reasoned estimate from someone who's studied the data. And he's not alone anymore. The Galileo Project, which Loeb founded in 2021, is building infrastructure specifically to detect technological objects, telescope arrays equipped with AI to identify anomalies, real-time tracking systems, independent verification. Science has been wrong before about what we thought was alien. Fast radio bursts turned out to be neutron stars. Pulsars were thought to be artificial beacons, until we understood their physics. Tabby's star dimming was probably dust, not megastructures. We've had false alarms. We've gotten excited and then found natural explanations. But each time, the evidence was ambiguous. This time, the data points in one direction consistently: the trajectory, the composition, the size, the survival, the brightening. And now, the blue light. In February 2025, JUICE's data downloads. The temperature readings arrive. The spectroscopy confirms or refutes. The images either show blue or they don't. And humanity either wakes up to the reality that we're not alone and we're being studied, or we find natural explanations that make all the anomalies disappear. But the blue glow doesn't lie. Physics doesn't lie. Something on 3I Atlas is generating heat that shouldn't exist, and in 90 days we find out exactly what that something is.